In the last lecture, we saw how the Fourier transform method can be employed to evaluate the transients in a network. A few comments about this method. Essentially, when we wish to find out the transient behavior of a network, it is generally after a switching operation. Let us assume that some excitation function is introduced into the circuit at t equals 0, and we wish to find out the response of the network following the switching operation. We shall make two assumptions. First of all, let us assume that the network is initially relaxed. That means it has no initial energy stored in the network, which in other words means the capacitors are initially uncharged and the inductors carry no current. This assumption of the network being initially relaxed does not entail any loss of generality, because if indeed there are initial charges on the capacitor and initial currents in the inductors, they can be replaced by equivalent sources, and these equivalent sources can be considered to be additional excitations, and the principle of superposition brought into play to evaluate the responses to the various excitations and adding them up to find the total solution. Therefore, we shall assume that the network is initially relaxed, and we are interested in finding out the response of the network following the switching in of an excitation at t equals 0. A second assumption we will make is that the natural response of the network is one such that it dies down to negligible proportions in course of time, and this is common to most networks that we deal with, particularly dissipative networks, and therefore, this once again does not seriously disturb the generality of the situation. However, the Fourier methods can also be applied where the natural frequencies of the network have 0 real part. In other words, there is sustained natural response, oscillations, sinusoidal oscillations or a DC component, but the analysis becomes a little more complicated, but we will avoid situations of this type in this course. That means, we will assume that the natural response decays with time. Under these assumptions, when we have a excitation switched in at t equals 0, we expect the response also to be 0 for t up to t equals 0, because the network is assumed to be causal, and therefore, any excitation that is applied at t equals 0 cannot produce a response prior to that. So, we expect the response to be 0 for up to t equals 0 and then become non-zero from t equals 0 onwards for positive t. Now, the Fourier method tells us that any such excitation function can be split up as the sum of tiny sinusoids starting from t equals minus infinity onwards and going up to t equals infinity. Now, each one of these sinusoids produces a response which can be evaluated using the steady state sinusoidal circuit theory methods, that is using these frequency response techniques, and then all these responses can be added up to find the total response. So, the sum of the steady state responses is what we obtain through the Fourier integral approach, and it turns out that the sum of the various steady state responses for the types of networks that we have talked about is also will become 0 up to t equals 0. So, this is as it should be, because no response can occur before the application of the excitation, and we further observe that if there are any natural responses terms produced at t equals minus infinity at the time where the excitation starts, all the sinusoids start from t equals minus infinity, all these natural responses will decay to negligible proportions by the time t equals 0 arrives, and this is the period in which we are interested in. We are interested in finding out the behavior of the network from t equals 0 onwards. That means, the natural response terms which might have emanated at t equals minus infinity would have decayed to negligible proportions when we come to t equals 0 onwards. But the sum of the steady state responses that we obtain will include transient terms, natural responses starting from t equals 0. That is what we are really interested in. So, the steady state responses will add up to 0 up to t equals 0, and from t equals 0 onwards, the response that we get, the total response that we get, include not only the forced response, but also the transient response or the natural response of the network starting from t equals 0. That is how it goes. Now, let us take a second example to illustrate the application of the Fourier theory to a network or a system which is characterized by its frequency response. So, let me take a filter network and see how the Fourier theory can be applied to this network. Let us consider an ideal low pass filter. And we apply a unit step function as its excitation, and we would like to find out what the response is. Now, the ideal low pass filter has a frequency response function like this. So, the frequency response function of the ideal low pass filter can be considered to be 1 for omega magnitude less than omega c and 0 for omega magnitude greater than omega c. That is, this is the kind of response function that we have. Now, under these conditions, this is the system function of the low pass filter. Therefore, y j omega, the Fourier transform, the output is h j omega, the system response function, frequency response function, times the Fourier transform, this is h j omega, times the Fourier transform of u of t, which is the input function. Therefore, this will be h of j omega times the Fourier transform of the step function is 1 over j omega pi delta omega. So, this is y of j omega. If you find the inverse Fourier transform of this, you would naturally get the y of t. This is what we are interested in. So, y of t is obtained as 1 over 2 pi from minus infinity to plus infinity of h of j omega times 1 over j omega plus pi delta omega d omega, sorry, e to the power of j omega t d omega. This is the inverse Fourier transform function. Now, we are integrating with respect to omega, and we know that h of j omega vanishes when omega magnitude exceeds omega c. Therefore, we need to carry out this integration from between the limits minus omega c to plus omega c, because outside the integral vanishes. Therefore, this minus omega c to plus omega c 1 over j omega plus pi delta omega e to the power of j omega t dt d omega. Now, we observe, as far as the second term is concerned, pi delta omega multiplied by e to the power of j omega t d omega. Now, the multiplying factor for delta omega, we can substitute omega equals 0 in that. Therefore, this becomes 1, and we are integrating a delta omega over the range which covers omega equals 0. Therefore, that results in pi. That means the result of this portion of the integration will result in pi, and therefore, that pi multiplies by 1 over 2 pi will become half, plus you have minus omega c to plus omega c e to the power of j omega t can be written as cos omega t plus j sin omega t divided by j omega d omega. Now, this portion cos omega t divided by j omega is an odd function of omega, and we are integrating between symmetrical limits from minus omega c to plus omega c. Consequently, this being an odd function and you are integrating between symmetrical limits minus omega c to omega c, the contribution of this portion becomes 0. Therefore, the contribution arises only from sin omega t by omega term, and sin omega t by omega t is an even function of omega. Therefore, I can write this as 2 times 0 to omega c sin omega t by omega d omega. That means this will become y of t becomes half plus 2 times, we must have also 1 over 2 pi from this, because 1 over 2 pi times this one we must have. So, 1 over 2 pi I must have. So, 2 times 2 pi 0 to omega c sin omega c t by omega sin omega t by omega t omega, or this is half of 1 over pi. This can be put as sine integral of omega c t. This can be put like this 1 over, because after all I can write this as this, I can introduce a t here and then d omega t here, and this can be thought of as sin theta by theta d theta, and once you have this taken as theta, the limit will become omega c t. So, this can be put in this form. Now, if you evaluate this, you have this is a constant dc term. As far as sine integral is concerned, you recall the sine integral will have a characteristic like this. It goes to pi upon 2 and minus pi upon 2. This is sine integral of theta, which we have thought of, we have discussed earlier. So, but this is multiplied by pi, that means this quantity will reach asymptotically minus half for negative values of time and plus half for positive values of time. So, if you add to that this half, eventually y of t will be like this. There will be some oscillations like this, and essentially eventually this reaches 1, and this is t, this is y of t. So, this will be the response of the ideal low pass filter for a unit step input. So, if you have a unit step input here 1, the output will be like this, and depending upon the cutoff frequency omega c for the low pass filter, if you make the omega c larger and larger, this will become more closer to the step function. That means the overshoots, the oscillations will reduce, and this portion of the curve will become steeper and steeper. So, the more the cutoff frequency of the low pass filter, that means the greater bandwidth for the low pass filter, it becomes closer and closer to this. But the interesting thing is, you are applying a sine wave like this. Actually, the excitation function is 0 up to this point, and you are applying, this is your u of t, but the response is non-zero for negative values of time. So, even before the excitation is applied, there is a response. So, this clearly shows that this is a non-causal system, and which means physically this is something which we cannot expect to achieve in the physically, and therefore, an ideal low pass filter that we are talking about here with this type of characteristic can only be approximated, it can never be realized in practice, because we believe that no physical system can give response even before the excitation is applied. So, this is a non-causal situation, and this is one way of showing that an ideal low pass filter of that particular characteristic is not achievable in practice. All one can do is modify these characteristics in such a way that this portion of the response is avoided. That means, all low pass filters that we can build in practice cannot give this type of response. It can only give a response, suppose this is the input, it can only start giving response from this point onwards, maybe something like this, but this can be avoided. That means, the ideal low pass filter characteristic cannot be obtained in practice. However, my point in showing this, giving this example is that Fourier transform methods can be applied to networks characterized in terms of frequency response as here, and this is a very convenient tool in such situations.